factoring by grouping is another factoring technique that I like to emphasize because how I teach factoring more difficult polynomials uh, relies on the skill of factoring by grouping, and it's a technique that I never learned when I was in algebra back when I was in high school, and it really I wouldn't say it hindered me too much because I got a graduate degree in math, but uh, I definitely didn't really know how to factor polynomials as well as I could have. And really, how I learned how to factor was more by a guess and check method, which is totally fine. But what I wanted to emphasize in my lectures is, well, there is a systematic procedure for factoring, and it will always work if you know how to approach it. But anyways, factoring by grouping is important. When we get into factoring trinomials. But anyways, what I wanted to start off with is what's the idea behind factoring by grouping, and how does it work? But basically, it was sort of like in the last video when I talked about factoring out the GCF. I mentioned that it was often called the reverse distributive property because basically, the distributive property is when I have a something out front, and I could multiply that into the parentheses across each of the terms. And that would leave me, in this example with 12x plus 16. But factoring out a common factor is the exact opposite. It's kind of like I'm pulling out that number that would have distributed in. And it's just kind of like the opposite thing. And the same thing is true with factoring by grouping. Factoring by grouping is a process which we sometimes call reverse foiling, which goes back to the process of multiplying out polynomials when we have two or three, more than two terms in each of them. And really, foiling was just a double distributive property, if you think about it, right? Because when I'm trying to FOIL, what I have to do is I have to take, say I have a plus b times c plus d, I would have to take a, multiply into each of the terms from the second thing, and also b would need to multiply into each of those terms. So I could think about that as two separate distributive property components. And actually, if you write it, you could write this in a different way. Usually we don't write it like this because this takes more writing than it did before, but basically that would be a times parentheses plus d plus b parentheses c plus d, right? And I'm kind of breaking that up into the two separate distributive actions which I just showed. And ultimately what that would leave me with is a c plus ad, because a would distribute to both of them, and b c plus bd would distribute to both of them as well. So how does factoring by grouping work? But basically, it kind of, if we have a polynomial which has this sort of resemblance where there's two different parts, each of which have a common factor, if we group them into two separate groups and factor the GCF out of each of them, we can reverse the process of foiling and turn it into a set of two binomials multiplied together. Because right here, a is common factor. So if you're kind of reading this equation backwards, you could factor out a from c plus d, and that would leave me here. And I could factor out b from c plus d, which would leave me with this. And once I'm at this part, now this is something that is a little bit harder to see, but notice that c plus d is a common factor in this new sort of thing I created. Because I went from having 4 terms to really 2 terms, because I had a times this and b times this, but there's really only 2 larger terms here. And c plus d is a common factor in each of those 2 larger terms. Now that c plus d could be factored out like that, because that is a GCF of this new expression, and that would leave me with a plus b times parentheses c plus d, and it would take me back to the start. But that's the essence of how factoring by grouping works. We're gonna, step 1, group the first 2 terms and the last 2 terms, kind of like that. And I'll often underline them just to sort of emphasize my groups. And what I recommend is putting them in parentheses. I forgot to include this in my little step-by-step thing, but if you have the notes printed out, go ahead and add that to your note. Oops, parentheses. It's late. I'm tired. I forget how to spell parentheses. I think that's good. You ever get really late at night and you just have a hard time doing simple things that You know, in normal circumstances, you would not struggle on. Anyways, and then says step 2 is to factor out the GCF from each group, which is what we did there. It says if the remaining binomial is the same, factor it out, aka what I'll often refer to it as finish the grouping, and then we can obviously double check ourselves. So let's do a few examples. That was all very abstract. Let's get into it with a few of these. So basically step 1 is to group the first 2 terms and the last 2 terms. And technically you don't necessarily always have to group it that way, but usually it will be built in a way that it makes more sense to group always first 2 and last 2 together. And you could put them in parentheses if you want, or underline them as I did before. I guess I'll go ahead and put them in parentheses like this. But you do want to be careful, because sometimes if there's a minus in between, you're not allowed to just insert parentheses anywhere within a polynomial. So what I often will do instead is just underline them like that. But anyways, that's step 1. Step 2 is to factor out the GCF from each group. So in the first group, notice that I have a 3x squared in common. And if I were to factor that out from the first group, let me put that a little bit further to the left. What I would be left with is a single x from the first term and minus 2 from the second term. And in the second group, whenever there's a plus in between, we're going to go ahead and leave that alone. Notice that 2 is a common factor of the second group. 2, and if I were to factor out 2 from those 2 terms, that would leave me with x minus 2. And so I'm kind of breaking it up into 2 separate GCF problems. And once I've done that, then we can progress to step 3, which recall said if the remaining binomial is the same, factor it out, or finishing the grouping. And so this is the next step. Notice that what I get after I factor out those GCFs is the same thing in both cases, x minus 2 and x minus 2. And if that's the same, we could factor out the x minus 2. We could either put it at the front or at the end. Usually what I like to do is just put it at the end like this. And basically the other parts will go in the first parentheses. And now this is a step that is a little bit hard to understand why this makes sense, but again, I'll try to say it one more time. Basically, this x plus 2 is a commonality between these 2 larger terms. And again, whenever something is in common between 2 terms, I can always factor that out. So I'm kind of imagining pulling it out, and I'm just pulling it out to the right here. And if that's, again, it becomes one factor, because when I'm factoring it out, all of those commonalities turn into just one thing on the outside. And what I would be left with is whatever's remaining, 3x plus 2, and that's why. Of course, I put them in parentheses as well. But again, this makes sense because if I were to multiply this out, I'd have 3x squared times x and 3x squared times minus 2, which is this part, and 2 times x and 2 times negative 2, which is this part. And again, you can see why we call this reverse foiling, because it's sort of it's starting with 4 terms, which is always the result of a FOIL. It's putting them back into 2 groups of 2. And there we have it. And now we are finished with our factorization by grouping. Cool. And often we write equals between each line to indicate that, from the first part, each step is equal, and that's another emphasis where if I actually do multiply this out, it should return me back to the start. But it's sort of a notation thing where it's not necessary, because this is not an equation, it's an expression, but it's just a way of saying, well, this expression is equal to this expression is equal to this expression. But if you don't write the equal sign, it's fine, because you're just kind of writing it kind of like in writing out a letter or an essay. You just kind of, anyways. I don't know why I'm talking about this right now. I'm too tired to go off on tangents. Let's do a couple more examples of factoring by grouping. And then I'll leave the rest for you to practice yourself. So in the next one, again, I would start with the first group and the second group. The first group has a common factor of a, leaving me with x plus y. The second group has a common factor of b, leaving me with x plus y. And again, what I am left with is the same thing. So I can complete the grouping by putting a plus b into the first parentheses and leaving x plus y in the second parentheses. And what I'm left with is a reverse FOILed expression, or again, we've factored this thing by grouping. Let's do one more. And I wanted to address the case, well, what happens if there is a negative in between? Because I mentioned that earlier. This is actually an important thing to remember. So in the third example, we have 27x to the 7th plus 9x to the 5th and negative 18x cubed plus 6x. And actually, there's a typo here I just realized, because if you try to do this one by grouping, it will not work. And oh, this is something else I wanted to mention. If you're wondering, well, what if after factoring out a and b here, what if these were not the same? And that's actually a really easy answer, because basically, if it's not the same, factoring by grouping doesn't work. It only works if your remaining part on the inside is the same. And here, that's why I recognize that there's a typo in the packet. Actually, I remember this because it's been in my packets for many years, and I just never remember to fix it. The proverbial thorn in my side. But anyways, just pretend that it said negative to begin with, because the example didn't work if that negative was not there. But anyways, from the first set, we have a common factor of 9x to the 5th. And if I factor out that would leave me with 3x plus 1. And remember, this is another thing that's easy to forget, is that if you're factoring out 9x to the 5th from 9x to the 5th, what's always left is 1, not 0. Because when you're dividing out something completely, anything divided by itself leaves you with 1. It's not like subtracting. And again, if I were to multiply it out, if I didn't put this plus 1 here, it would just leave me the first term, and the second term would just poof. So, you know, that's another thing easy to miss. Now, from the second group, and this is the thing I wanted to mention, is whenever there's a negative in between the two groups, you always need to factor out a negative from on the second grouping. So basically, the negative is going to have to be factored out. Also notice that these have a common factor of a negative, but actually that won't necessarily be the case. You know, so there can be ones that are a little tricky. But anytime there's a negative in between the groups, always factor out a negative, regardless if it's common or not. And then from the rest of it, it appears as though 6x is common factor, which would leave me with 3x plus 1. And again, if factoring by grouping is going to work, you know that this one has to be the same as this one. So that's something else that can help you as you're practicing some of the examples in my math lab. And then I need to complete the grouping, which would leave me with 9x to the 5th minus 6x and 3x plus 1. And technically, there's actually more I could have done, because the original polynomial had a common factor, or if I'm looking at this factor, I can see that there's still a common factor in here. And whenever you have a common factor, you should factor it out if you're trying to do it. The instructions didn't say to factor completely, but we'll talk about a general factoring strategy later. And sometimes there's more that can be done even after the first couple steps. And this should be a B. I just realized my B is kind of looking like 6 right now. So I apologize for that. Anyways, that will wrap up my talk on factoring by grouping. I'll leave the rest for you to try on your own. I'll do one more video and talk about factoring trinomials by what I call the magic X method. But the magic X method is a way for factoring out polynomials that, you know, quadratics are what we often call them, or, but anyways, it's another factoring strategy, very critical, and basically all of this stuff we're going to talk more about in live class, and we'll have our class activity will be on this sort of thing as well. But basically, I wanted to teach you the basics of the magic X method, because in class I wanted to get at how do we put this all together to be able to factor basically any trinomial, which is a little bit tricky, but that will wrap up this one.